Claudio and Nikolas, being along with many other people at the Gali, have been working a lot around QA, the infrastructure, the efforts around gardening, basically everything on why and how we manage to keep this beast under control quality-wise. So whenever you want to start, you can do.
Hello, can you hear me?
Yes, they can hear you.
Okay. Hi everyone, welcome. I am Claudio Saavedra. I will be presenting this talk together with Nikolas remotely. I have been in Italia for quite a long time, almost 20 years, and working on WebKit for pretty much almost all of that time. Before that, I come from the GNOME world, where I was involved in the Epiphany browser, the image viewer, and other things like that. And lately, mostly I've been working on tightening the code of WebKit, making it safer in different ways. And that has evolved also into being more involved into the QA part of the GTK and WPE ports. And Nikolas, if you want to introduce yourself, now is the right time.
Yeah, thanks. Can you hear me properly?
Yes.
Good. So yeah, I'm Nico. I'm a Guardian since 2019. Been a long time WebKit contributor since more than 2 decades now. Also a reviewer, and I was working a lot on SVG stuff in the past years. Yeah, and today we are going to look at a specific aspect. You notice this catchy talk title, No QA, No WPE, how we try hard to catch regressions before you do. So today in this talk, we want to focus on 3 things. One is to show you how WebKit is actually tested, what we do, what is the CI pipeline, the bots, test suites we run, etc. Then a few words about the infrastructure behind it, and finally Claudio's part about the daily gardening, monitoring, and performance results. So let's just get started since we are a bit over time. There should be a background image here. I don't think you can see it. Can you? No. Okay. Let's just go on. So the heart of our CI is BuildBot. It's a Python-based CI/CD framework, and its setup consists of multiple components. So important to know is there is a master machine hosted at Apple, which schedules the work and knows every builder. So what is a builder? A builder is a named queue that, for instance, WP Linux 64-bit release build, which runs or compiles WP in a certain configuration. Here on Linux with release configuration. And a queue can be served by one or more workers, and a worker is anything, a machine, a container, whatever, that has the BuildBot worker client connecting to the BuildBot master. And then when there's a push to the main branch of WebKit, it receives a notification that there's a job pending, and then the worker in such a builder takes that job, executes the steps that are predefined in the WebKit repo, and comes back with the result. So for WebKit concerns, we have 2 separated CI systems. So one is the EWS, one is the post commit. We're going to have a closer look at them. So the big picture, 2 tiers of CI. So whenever you open a pull request on GitHub to make a change to WebKit, first of all, that change goes through the EWS system, the early warning system. The intent is to catch regressions before they actually land. You can see here a screenshot of the so-called EWS status bubble, which is posted on every pull request. Here in that particular bubble, you can see it includes various of tests, for instance, whether you correctly stick to the coding style, whether there's any regressions in the Perl tooling, Python tooling, whatever. And most importantly, it goes through build and test steps. For instance, in this kind of PR, you can see there's a green arrow at the WPE cell, which means the compilation worked, but WPE WK2 is red, a red cross, which means the tests are not passing. So you better not land that change, because otherwise you will introduce a regression. So this system is the tier 1. EWS pre-commit. So the purpose is to build and test every single pull request before it gets merged. So the feedback is directly given back to the PR in form of that status bubble, so developers can quickly see if there's anything problematic with their patch or not. So the scope for testing is here limited because we need to be fast. You don't want to wait 8 hours for an EWS result to appear, but it should come quickly. You can quickly iterate on your patches. So for WPE specifically, we have 3 queues running. One is the build queue that you saw before, the first entry. Then there is the test queue, which runs the layout tests, more on that later, and the API tests. The tier 2 is the post-commit one. The idea here is to build and test changes after they land on the main branch. But there's a caveat, because the scope here is full and exhaustive. So we run many configurations, many test suites. So to get the post-commit results for a certain commit, it takes time, maybe 5 hours, 6 hours, 12 hours, whatever. So for that purpose, build requests for a single builder are coalescent when bots are busy, which means one of the post-commit builds can actually span several commits. But that's still okay. It gives you a range. If there's a regression on a certain build configuration, you don't need to go through months of work, but maybe 6, 7, 8, 10 commits and identify the one which caused the regression. Results are uploaded and aggregated on a special dashboard, results.webkit.org. And we currently run in the post-commit setup 24 bots, testing various build and test and performance configurations. Release, debug on ARM, 64, 32 bits, Clang, etc. And what do we test? We test various things in the post-commit area. One thing is the C and glib API, which you can also test locally when you have the WebKit container SDK set up. You build WebKit, you can simply invoke the same commands that are highlighted here, and it does basically the same job. Run WPE tests, run API tests. You can check JavaScript core by probing the JS engine correctness, ECMAScript conformance by run JavaScript core tests. There we have a test runner for test 262. WebDriver, the very important run WebKit tests command, which runs the tests the basically the whole page rendering and web platform behavior, including WPT tests. So that's about 90K tests. We have specific tests for WebDriver, MVT. These are media-focused tests covering stuff like MSE, EME, etc. And performance. So the goal for all of that is to identify regressions automatically. So we want to answer the question, does this change introduce any new unexpected failure? For performance testing, as you know, we at Igalia care a lot about embedded devices. So our reference platform for performance testing is the Raspberry Pi 4. We have 16 of them in a farm, and we have a specific build queue for WPE that does a cross compilation using Yocto to build WebKit for the Raspberry Pi 4, once in 64-bit and 32-bit mode. And then we run those images on real Raspberry Pi 4 boards with the mini browser in full screen on a real GPU on a Wayland Weston stack, and then run benchmarks. So the focus here for us is on MotionMark 1.3.1, Jetstream 2, and Speedometer 3. These are the ones that we keep monitoring. You can see and visit the performance dashboard and see it on your own. So the Buildboard workers basically push the performance data here continuously. You get benchmarks like the one that I'm showing in the next slide. For instance, this is an example of MotionMark 1.3 running at 50 FPS, showing the overall score of the test result for the CPU and GPU rendering path. You can see with the blue dots extend to the beginning of this plot, the yellow ones not, because we are not running the CPU configuration all the time, but we did so with the GPU configuration. And it's at 15 FPS. It's a custom patch on top of MotionMark, basically to reduce the frame cadence a bit and give them more time to render certain frames. So the scores that you can see here, if you run MotionMark yourself on a Raspberry Pi 4, they would be much lower. That is because we specifically reduce the frame cadence. because we want higher numbers, high scores here to be able to detect regressions more precisely than if you would have a low baseline score of, let's say, 2 or 3. We rather want something like 300, 400. It's just a choice to make things for us easier. And this is real data, so you can see 2.5 years ago, basically somewhere in June 2024, MotionMark gave something like 300 points score on a Raspberry Pi 4, and we have tripled the score with all the graphics and rendering efforts that we did so far. So now you get about 900 points score in that specific benchmark GPU rendering. And you can also see the WPE releases here as red markers. So you get an idea what kind of performance you can expect with this WPE release. Furthermore, we also check in the performance testing important metrics such as CPU utilization, RAM consumption, GPU load. Because the score is one thing, but knowing how to get there with what kind of resources that we need to consume for that is another story. It's equally important to understand whether a certain change gives you just a better score at a trade-off of like double GPU load, or whether you get a better score with even reduced GPU load. So this is really important for us. You can see here in these patterns that we run MotionMark 3 times. So a job run for us is run MotionMark 3 times. You can see these patterns, for instance, in the RAM consumption pretty easily. You can see the RAM consumption is growing a bit and then drops. It's growing a bit and then drops. These are the 3 MotionMark runs, and you can see this in all the data points on the dashboard. Whenever you're going to run, you get this kind of instrumentation for everything. So now I want to talk a bit about the infrastructure behind all of this, since we revamped all of the infrastructure in the past almost 2 years. So first we introduced this SDK so that all developers have a consistent environment for testing. Then we made it possible that we can use the same SDK container images also on the bots everywhere, so that when you work on WPE on your laptop or whether tests are running in the CI, it's all done on the same base image, same system, same whatever, versions of all the software. We used to have a manual setup, like having some bare metal machines at Hetzner, which were configured manually, and it was not fragile, but cumbersome. So when a machine needed a replacement, it was a lot of work. Now we moved completely to an infrastructure as code approach. So we set up a Kubernetes cluster running on Hetzner hardware. All the software that we deploy to this cluster is managed by Helm charts. All the infrastructure, each server, each service is described by OpenTofu, which is a way to specify the state of a system in code, in YAML files, basically, declarative. And finally, the OCI containers, in which we then later on run the SDK, in which we execute the build and test steps. So just a few words about the cluster topology. So we have a high availability Kubernetes cluster across 3 data centers that Hetzner provides, one in Frankfurt, in Nuremberg, and Helsinki. So this, even if one goes down, this Kubernetes infrastructure survives. We have some nodes for the infrastructure where we run like non-build-board worker pods, and then 2 interesting things: a dedicated bare metal pool. So that consists of 12 AX102 servers at the moment, 16 cores, 128 gigs of RAM. They are always on, connected to the Kubernetes cluster. And the primary purpose is to run the build-board worker pods, which can be any of the build-board queues that you see in the CI. But we also have this blue thing here, this green thing, the auto-scaled build-board pools. This is a way to scale up cloud instances whenever we need capacity. Consider the case when EWS is very crowded, a lot of people are uploading patches, and if you would only have a certain fixed set of workers, people need to wait. So this is a way to give extra capacity to the cluster, but scale down as quickly as possible to save money, basically. So the main algorithm, how all of this works, is we basically have a service running, the build-board monitor, which periodically looks in build WebKit org for each of the builders, how many builds are in the queue right now, running, pending, and how many workers are connected right now. So if a queue is idle, there will be no workers connected. So we scale them down to 0. Now someone pushes a patch and there's something queued. The build monitor will notice, hey, there's a missing worker, we need to scale up one. The autoscaler kicks in, will do that, will start a new buildbot worker pod, which will auto-connect to the buildbot master and attach to that queue. So now one is working, and then another push appears, and another person uploads a patch, and the same thing happens. So this is continuously running in a loop, and we first try to fill out our bare metal resources, and if that is exhausted, we can then still fall back and add some cloud instances to the mix to make it very fast for the developers to get their, for instance, EWS results, and also to have well, a very responsive kind of system, and also fully replaceable. Even if all our bare metal servers would die in the same moment, other cloud instances would take over, making this a reliable CI system. So that's it for my part regarding the infrastructure, and I would now hand over to Claudio, who will tell you about keeping the bots green. Thanks for your attention.
Okay, looks like I'm sharing the screen correctly. So yeah, thank you, Nikolas. Now, all this infrastructure without the human touch will not be sufficient. There is also work that needs to be done to make sure that whenever something doesn't work in the way that we want it to, then we can act quickly and try to resolve the issue. So this is where gardening comes into play. Now, what is gardening? Well, if you have a garden or a house with a garden, you know that you need to continuously be on top of it to make sure that there is no disease on the plants. And usually what you do is that you go around and you check that everything is looking green and nice. And if something is not, then you start diagnosing what the problem is. So this is where the analogy comes from. In particular, in WebKit, we have a cadence of about 80 patches per day. And most of the time, they don't introduce regressions because of the EWS system that Nikolas described is already sufficiently robust to detect most of them. But every once in a while, something slips in that can cause tests to start failing that were not failing before, or some other unexpected regression. So gardening is the continuous work that we do to make sure that when this happens, we detect quickly and fix the issue. First step is to identify the issue and try to find what commit introduced it, then update the expectations so that the system knows that this is not unexpected to fail, and at the same time start investigating who will be the right person to fix this. The person doing gardening is not usually the expert to solve this, but can detect, for example, is this a multimedia issue? Let's talk to multimedia people. Or is this a graphics issue? Let's talk to the graphics people. And yeah, and that way we can keep the tree green. Now, this work entails 3 different things. First of all, the build health, because as Nikolas was describing earlier, we have many different configurations we care about. Not all of them are tested in EWS, so patches can land that are completely green in EWS, but that break up, for example, ARM configuration or with a different compiler or in a stable Linux distribution. And for that reason, we need to also keep an eye on those builds and make sure that they are building correctly. That's what build WebKit.org is for. It's a nice dashboard that has all the post-commit build and test results. Then there is also the test results. We aim to keep the test results green, or the test suits running green, but whenever one turns red, we need to keep an eye and have a look what's going on. And then the third thing, of course, is performance, because even if you have correctness in API tests, in layout tests, in JavaScript tests, that doesn't necessarily mean that there are no performance regressions. So that's where the dashboard comes into play. So I want to share an example of how this gardening can help to detect and fix regressions quickly. So May 28, this is a real life example. Few weeks ago, we decided to remove some things that were left in the tree that related to the Flatpak tooling that we used to have before the current SDK. So just a cleanup, and the code was reviewed, it was approved, it landed, but in the post-commit queues we noticed that, okay, some issues appeared with the JavaScript and the test 262 suits. The gardener noticed this, filed a bug, and noticed that this points straight to a particular commit, which was the one that removed the Flatpak tooling. We talked to the person who made that change. That person checks, notices what the issue is, and the same day fixes it, and then we have again a green JavaScript and test 262 runs working. So, and then another example that is, I think, very interesting is a performance regression, because this is different. For this, you need to keep an eye on the performance dashboards, and it requires a bit of I'm going to show you better how we notice. If you look at the red line on the left, you can see that there is clearly a drop in performance around, I'm not sure if the dates are there visible, but around May 19. So this was already a red flag and something that we needed to do something about. And it was not so difficult to notice that the issue was caused by a change introduced in the WTF component of WebKit, where all the data structures are, particularly to the variant one, that an Apple developer made some changes that optimize how the build time of variants, saving up to 5% of build time. It was reviewed, approved, landed everything great, except for this that we detected a few days later. Motion marks started showing performance decrease, in particular in the Raspberry Pi 4 GCC bots. And GCC is particularly relevant in this, because the main issue there was that these optimizations were relying on some Clang features that I'm not going to go into detail into this, but basically for GCC, instead of having jump tables that are very fast, we had instead of linear branch cascade, which basically means a massive amount of comparisons especially for large variants. And in particular in the graphics side, this playlist used a very big variant that, well, it requires a lot of comparisons in that case, and that's what caused this regression. We managed to fix this by targeting particular this GCC variant of this data structure to change it to how it was before and make sure that it can use jump tables and keeping the Clang implementation as is. And then after that, the numbers go up, everyone is happy, and the performance stays good. Now, what's the status of the bots currently? EWS generally green, so everything is healthy there. If you send a patch and it's red, it very likely means that it's because there is an issue in the patch that needs to be investigated. There are rarely false positives nowadays. We are trying to avoid that from happening. In terms of builds, also very green most cases. And in the case of the tests, this is where things are a bit interesting right now. They are not entirely green, but this is on purpose. This is not because we're not doing a good job. Things were so well recently that we decided to take it one step further and enable assertions in the release configuration in post-commit bots. What does this mean? It means that WebKit is full of assertions everywhere that check for correctness, and when those assertions are enabled, WebKit is going to crash. And the idea here is that we can detect where we have issues with correctness in the code that otherwise will go unnoticed and can cause other side effects or bugs that are much harder to detect. And so we decided, okay, let's enable that in the bots, in the post-commit bots for the release configuration. And now we have some unexpected crashes. Every run has about between 1 and 5 crashes, I think. And this is good. This is good because it means that it's not a big number, and we are currently working on investigating those, triaging them. Sometimes assertions can be outdated and they just need to be updated or removed. In other cases, there are real bugs that need to be fixed. So this is allowing us to make things even more stable. So I think it's a good status of affairs. Yeah. So starting to sum it up, if you look at this all together, you see that in order for a bug to get to a stable release of WPE, it's actually tricky because there are so many layers that make sure that this is prevented. First, at the CI level before a patch lands, then after it lands, with the continuous gardening work, we try to make sure that we detect them promptly. And then there is another nice thing with the synergy we have with WebKit GTK, the GTK port of WebKit, that a lot of the code is shared with WPE. And because of the dynamics of how Linux distribution adopt the releases of WebKit GTK and release them to the public, we get a lot of feedback as well from there. So very often the more serious graphic related, for example, regressions are detected there, and that's way before we get to see them in production in WPE based products, for example. So this synergy is very healthy. And also, as of recently, we are doing a lot more extensive testing also of the stable branches of WPE to make sure that whenever we backport fixes, either security fixes or bug fixes to the stable branches, we also test layout tests, API tests, and before we ship them. And to finish, what's next? So currently we are only testing the ARM64 architecture in post-commit, but we are currently working on deploying as well in EWS, so we can detect specific issues that only pop up in ARM64 before the patches land. And for the performance testing, we are currently testing mostly main, and we want to also start doing this in the stable branches because it's important that nowadays we land a lot of security fixes in stable, and it's good to make sure that those security fixes, even if they are necessary because, well, they catch security bugs potentially, we need to make sure that also they didn't cause regressions, or if they do that, then they're actionable and there's something we can do about them. Nikolas, do you want to?
Yeah, I can sum it up. So no QA, no WP. It's very easy. So we need those two tiers of CI. We have 24 queues in the post-commit, 16 Raspberry Pi boards, and do 365 days of gardening. Okay, that's maybe a bit exaggerated, but at least we have an active assigned gardener Monday to Friday. So a person at Igalia looking at the trees, doing an extensive checklist, and every day we have a ticket and report. So we are meeting every week to discuss the state of affairs. And we need this. If you take away any of those layers, we have something that will slip regressions through to our customers. So that's a non-go. So no QA, no WP.
And thanks. I think we're a bit over time, but if you have any questions.
Actually, we are okay because you already started 5 minutes late, so I think we can assume
okay.
5 minutes delay. So if you have any questions.
Then there is time for questions.
Yes. But maybe just playing everything perfectly. Yeah. Okay.
There's a microphone.
Okay. Hey, I want to ask, currently on your CI you do a lot of testing with Raspberry Pi based ARM. Are you planning to add more embedded devices besides Raspberry Pi you can run tests on?
I don't think at the moment we have any particular plans. I think it's proven to be a good baseline, but I guess if there are other.
It's actually a good question. I mean, at the moment we do at the moment we do have the Raspberry Pi 4, but and Claudio's right. I mean, at the moment we don't have anything specific that we can tell you like we are going to do this and when. But we've been discussing internally the possibility of supporting other boards. The thing is that we picked the Raspberry Pi 4 because it's kind of a reference board, so everyone can easily get it and it's easy. The truth is that in the industry, customers, many companies, they use specific boards which has their particularities. So it's kind of impossible to cover them all. So we've been discussing internally, maybe we could do in collaboration with customers or companies, this possibility of integrating other boards into these kind of systems. But we will need, in that case, kind of support for that. But yeah, it's been discussion, but there's nothing specific right now. It's been an ongoing discussion. I don't know, Alice, if you want to, or you want to clarify anything else, because it's something that we've been discussing internally. But
Yeah. We are thinking about it, but it's true that we are already testing in other platforms that are not there. That's ours. And we have continuous integration in other customers with different boards. But those integrations are specific, but we try to keep everything in the same scenario. So we kind of feel like this is our part, and then every customer is pushing some of them. But it's true that maybe at some point we add some more board that we see that every customer is using for some specific situation. But in the end, we try to balance the amount of work that we do and the amount of information, because sometimes it can be, maintaining all that infrastructure, we really need to take a lot of different effort to automatize as much as possible. And actually that's our plan. With all this effort, in the future, I hope we really are able to do even more and add more things if we are able to automatize even. For instance, all this gardening effort is still too manual, and we have developers spending time checking things. Yeah.
Thank you.
thank you. And
So I have 2 points actually. So the first is obviously big part of the browser's input events and interaction. So my question would be, how do you deal with tests that require user input, like performance tests, especially like continuous input, like scrolling or interacting with some paint application or moving a window on the screen? So do you have any automation in place for that as well? Ideally, you would want to test the entire stack from, let's say, touch controller via compositor to the browser, rather than maybe injecting something via WebDriver, for example. And the other thing is that regressions might emerge very late in the pipeline, and some stuff might only become apparent when you actually observe the visual result. For example, you could have improved your average frame rate, even reduced the resource consumption, but you might have introduced some, let's say, periodic lag on some animation. So this is obviously less straightforward to automate, if even feasible in some cases. So have you any thoughts on that, or any additional tests in place for such cases?
Go ahead.
yeah, Nico, go.
Yeah, very good questions, Georg. So indeed, for an end-to-end testing of the whole product, including scrolling, latency, and whatever, this is something, it's hard, but we need it in the end. So, but it's not currently planned in that kind of CI. Regarding your other question, we actually have a different CI that we didn't discuss today in the Meta WebKit Yocto layer directly. And there are additional tests executed that, for instance, take screenshots. So it's not perfect, but at least we notice during motion mark runs, for instance, if there's a visual glitch, across all the frames. For instance, we had situations where there were color channels swapped, which nobody noticed except in those tests where you could see it in the screenshots. But I agree that is a weak point, and it would be nice to have more automatization. And for instance, for frame rates, it would be really interesting to look at distributions of the frame rates instead of just average frames per second. but noticing like the distribution of the frame rates in a histogram and watching the 95 percentile so that you could see whether anything is improving or adding in regressions there. These are things we have on our mind, but no concrete action plans yet.
Okay, I think we are out of time. If there's any 1 second question, we can do it. Otherwise, yes, thank you everyone for the presentation.
Thank you.
Thank you.